Hi everyone, my name is Evgeny Stemasov and I'm here to present, on behalf of my co-authors, our work on pARam, which is a design tool for personal fabrication that focuses on the interaction with parametric designs in extended reality. First of all, a brief overview of what we did. Users can configure a design for fabrication, as you can see here. They can change specific parameters. They see an in-context preview, and they can evaluate their design within this future context. Now, to understand why we built this, it's important to understand how you might be designing objects that you may want to fabricate. Fabrication devices like 3D printers are, by now, accessible means to manufacture objects, but they require inputs, designs, basically. There are several aspects to designing. Users have to design something physical, using only digital media. They often design at a disconnected workstation, not at the location of use. They have to understand and encode requirements they or their environment may have, and ideally they have to understand physical effects that their design may have early on, or alternatively fabricate prototypes to test. In the context of personal fabrication, there are two ways to succeed here. The first one is 3D modeling. You use an often complex software to define each detail of a design. A popular alternative is searching for something to fabricate. People share various designs on pages like Thingiverse or Printables. You don't design anything here, you search and find and fabricate something. These approaches are opposites on a set of spectra. One is complex but expressive, the other, less complex but also probably less expressive. There are also approaches that try to provide some sort of balance between these extremes. Specifically, we see this in customizer tools, where users may remix a predefined design rather easily. So Thingiverse provides such a customizer interface if the authors of a design have provided a parametric representation. So we have this loop of a user changing parameters, mostly depicted with sliders or text fields. The interface also shows a preview, and the users can decide to change more parameters or download and fabricate their design. There's also the notion of parametric modeling. This is about defining, authoring these customizers or other models that respond to parameters. This requires expert designers to embed their domain knowledge in a dynamic representation that changes and remains valid. The focus of our work is on this interaction with parametric designs through non-experts, not the authoring of them. And this interaction with parametric designs already manifests in different tools and practices. We have these customizers interfaces, people remix them, but also there are product configurators, for example. And to further highlight how this is a practice that is already happening for many users, I'd like to show you how a parametric design can be already found outside of expert domains like architecture or hobbyist domains like personal fabrication. So what you see here is a user-facing parametric design. We are configuring a shelf to store records. As with the example before, our interface is reduced to relevant parameters. It provides an immediate preview and it's reasonably easy to use. For example, we have parameters that provide options, as you can see here. We also have dimensions that are reduced to steps here. They are basically discretized. Or we have something more continuous with quite a few steps to choose from. What's interesting here is that some choices trigger warning regarding the fabricated outcome. And there are more immediate consequences of the parameters that we change. Here we see the cost changing depending on what we have picked. And lastly, we still have this preview, which shows us human silhouette as a reference and some sort of default room that is supposed to describe a context. This example also ties to a long history in academic research, where approaches to parametric design, design tools for personal fabrication, and design tools that use extended reality have been developed and explored. We have various approaches that discuss how we author and interact with parametric representations, for example. There are also various tools in the context of personal fabrication trying to make design as such more approachable to novices. And there has also been extensive research into design tools that either leverage XR for design or describe design tools to author XR experiences. There is quite a bit of conceptual overlap as we're designing or authoring 3D artifacts, both for fabrication but also for immersive environments. Looking both at the literature and this existing status quo in product configurators, we settled on these three high-level design goals. We want to enable in-situ interaction with parametric designs or customizers. We're dealing with designs that will be fabricated and therefore are intended for a specific location or environment most of the time. We also want to support users in choosing correct or fitting values for the parameters. They should be able to navigate and understand this design space that each customizer provides to them. And lastly, we want users to understand the consequences of their choices early on, before anything is fabricated and tested. So the first design goal manifests in us using an AR headset to unify the space where we design and the space where we'll be using this object that we design. The second design goal is addressed by a set of support mechanisms to choose and define parameters. And the last design goal manifests in a set of estimation functions that tie the user's environment into the process. Let's talk about our proof of concept implementation, which we named pARam. In total, we had 15 designs available and implemented. We have some shelves, vases or lampshades, and a few tables. These are all household objects that benefit from being customized, either to achieve a user's desired aesthetics or functionality. pARam was implemented using Unity, the Microsoft HoloLens 2 as a platform, MRTK for interfaces, and the Archimetics asset to create the individual designs. I'd like to start with a brief overview of the interface, and then we'll walk through the individual functions. We, of course, have a preview of our design that we can position freely in space. We also see sliders known from other interfaces to control individual parameters. These spheres on and around the model are handles for direct manipulation. The UI also shows buttons to trigger measurement modes, and it also shows entries for the estimation functionalities. Let's start with input and input support. As mentioned earlier, we have a pane with sliders to control parameters. Each has a name, a value display, and can be changed across a predefined, constrained range. We can also grab handles on and around the model for direct manipulation. Changes here are generally reflected in the user interface and vice versa. When we have designs that have curvature-related parameters, it's also possible to sketch out the desired shape in midair, and this is then converted as good as possible to a set of parameters to match this curve. A basic functionality of parametric designs is ensuring validity through constraints. Here we see a user temporarily violating such a constraint, but a valid state is restored as soon as the user lets go of the handle. Users can also use gestures to measure objects or estimate sizes. They can use either two hands or the thumb and the index finger on one hand. They get a live value display and can use a voice command to immediately transfer a measurement to a previously chosen parameter. For objects that are ergonomics related, like this bench, users can configure profiles. Based on that, pARam shows ideal value ranges that are grounded in literature for a fitting result. They are visualized in orange here in the UI, and the user can choose to accept or ignore them. What we can use XR for is to preview and interact with our designs in their future context, in their physical environment. We've seen this in the previous examples. However, there is much more than we can get from these platforms. Specifically, HMDs have a degree of scene understanding, and this can inform our design process, for instance by using the scanned environment mesh to simulate and estimate specific aspects of our design. We can use that, for example, to try and understand whether a design might topple or not on a specific surface. Now, what you see here is not a simulation, but this can serve as an early lower bound for balance. So the model is taken and dropped onto this scanned environment mesh with kind of a default configuration. For lighting-related designs, we can try and evaluate lighting and shadowing patterns in relation to the environment. Again, we would not consider this a simulation, but this can inform the design process anyway. This is how it looks like, and as before, we take the scanned environment mesh and project this pattern onto it. And when you go through the entire pipeline until fabrication, the result mostly matches what we expected. We then went ahead and evaluated pARam in a small user study. We had 20 participants, with a bit more than half with prior experience in either 3D modeling, AR/VR, and product configurators. The procedure involved participants solving two tasks, configuring a bench or a lampshade. Users had measuring tape, rulers, calipers, all of that available to use. And we also compared a desktop-bound approach to an XR-supported approach. So the look and feel of these two variants was comparable, and we tried to achieve feature parity. Functions like the lighting simulation were also included, but they used a default cube-like room as a replacement for something that is scanned or real. This is how the training task looked like. A simple book holder designed with 3 parameters only. It looked reasonably similar in both AR and on the desktop, and users could familiarize themselves with the application and basic interactions using this. Let's briefly look at some of the results that we had. We asked participants about preferences they may have regarding which variant to use for which type of object. The desktop variant was, for instance, preferred for more complex objects, objects that require precise measures, or functional ones. For objects that, for example, are decorative or positioned in a specific known place, users expressed preference for pARam. We also logged individual interactions that users had while designing. So some differences were visible when we compare the desktop and the AR versions. But there might also be difference between people with prior experience in 3D modeling compared to novices. We denote those with a check mark or a cross for each line in the following plots. For example, we saw that pARam had a more even distribution between handles and sliders, while the desktop variant skewed towards slider-based interactions. And we also see this when we plot this over time, with experienced users potentially having a higher frequency of interactions. When we observe the actions and functions used over time, we also see that estimation functions were mostly used later on as kind of a validation step. We also see that experts measured earlier and more often, especially on the desktop. So for the discussion, I'd like to briefly touch on 2 points. The first one being the notion of this spatial interaction. We're defining objects for a specific context, and with pARam we can do this in that specific context and environment. We're also defining 3D objects, which may afford spatial interaction techniques, but this comes with its own trade-offs. The second one is related to the measurement functionalities. Measuring is a skill that you have to acquire, and the measurement functionality in pARam seemed to be received very positively, but it communicated a precision that it didn't really afford or provide in the end. So users were rather confident using it, but did not always succeed with it. To wrap it up, we presented pARam, a design tool that enables in-situ interaction with parametric designs in the context of designing for personal fabrication. We do see a set of limitations in the work. First of all, the estimation functions are rather rudimentary, and there's room for improvement here. Now, this was a conscious choice, as we wanted functions that need no setup, no preparation, and most likely no domain knowledge. There is also limited object set that we work with. In the user study, we did not cover users choosing the right parametric design, nor did we have users actually fabricate the designs. And lastly, we focused on interactions, not authoring. However, with tools like pARam, authoring parametric designs may become more complex, as designers have to encode and embed even more detail in these customizers. For future work, we'd like to expand the model set that is available to pARam. This in turn requires means for searching and choosing fitting parametric designs before we even get to customizing them. We also see a lot of potential in weaving more automation into tools like pARam. The precision of the gestural measurements could improve with that, for example. And more estimations, maybe higher fidelity ones, if and only if they need little setup, maybe ones that incorporate aspects of the fabrication process, would make sense in this context. To conclude, parametric designs reconcile ease of use and expressivity in many ways, and situating the interaction with them can incorporate more of the context in the configuration process. And with extended reality, we can do much more than just visualize designs in context. That's it from my side. For more details, please refer to the paper. Thank you for listening, and thank you to my collaborators.